Okay,
Thank you.
you're welcome. Okay, so here's a screen which has to do with another class. And all I need to do is add a page, put some lines on this thing, and we're ready to roll. Okay, questions before we get started? Anyone have any questions? Could be just small things from class, or could be problems. I'm fine with doing a problem too. And if you prefer, we can do it after class. So it's either now or later. It's okay, either way. Nothing? Okay. Well, let me sort of consolidate where we are now. We've learned a lot about the two-state Markov chain. What have we learned? We've learned that it could be described in terms of three properties. So let's list what we know about the two-state Markov chain. That's no good. That's better, I think. So, oh no, that's not going to work. Okay, I mean, no problem here, folks. The problem may be that my OneNote is not working. So, oh no, I don't know how to teach without writing. Oh God, this is a different problem. So let me see. The odd thing is I can go to any page I want, but my stylus isn't working. Apparently. All right. Technical problems to start the day. I'm going to just undo it again. Hope for the best here. So let's see what I can do. Let me shut it down. That's a little more promising. I'm just going to have to restart it and hope it works. Yay. Okay. So that seemed to have worked. Okay. I was going to be in trouble. Let me see if I can share it with you now. Share screen. There it is. Okay. All right. See if I can erase as well as write. Yep, I can erase and I can write. Okay, so what was I about to say? I was about to say that we can characterize a two-state Markov chain by three things. So we know there are, well, in terms of its initial distribution. Which we think of as this way. Day 0, you're either broken or working. And the probability of these things are given by this notation, P0 at 0. I'm sorry, pi 0 at 0 and pi 0 at 1. These are probabilities, they add up to 1. Okay. So we assume there's some kind of initial distribution. What else do we assume? We assume that there are transition probabilities. Probabilities. And in this case, well, we can represent them in different ways. We can represent it in terms of a diagram. The two states we denoted as 0 and 1. And you could say the transition from here to here is P. The transition from here to here is Q. The chance of going from 0 back to itself would be 1 minus P. And the chance of going from 1 back to itself is 1 minus Q. And what do we know? We know that P and Q are probabilities between 0 and 1. And that's pretty much it. Oh, well, there's different ways to write these. So you can write it this way. The transition from 0 to 1 is the probability that at some time n you're at 0, and in the next day up n plus 1 you're at 1. And we can do the others in a similar way. So the probability of going from 1 to 0 would be the transition of assuming that at some day n you're at 1, and the next day up you're at 0. So this, going from 0 to 1, is what we call P in the diagram. And going from 1 to 0 is what we call Q in the diagram. And there are two other transition probabilities. You can go from 0 back to itself. And that's the conditional probability at some day being at 0. And the next day up, you're still at 0. In terms of the picture, that's the loop here. That's 1 minus P. And then finally, the last transition probability in this case would be going from 1 to 1. And so that's the probability that at some day you're at 1, and at the next day also at 1. And that would be 1 minus Q. Now, by the way, if there's anyone dyslexic in here, this could be a little confusing because this is going from 0 to 1. So you're going from here to here. But when you write it in terms of conditional probability, you sort of read it the other way. This is what you assume. You started at 0 and you're going to 1 after 1 day. So the order here sort of gets reversed when you put it into conditional probability. This is starting from here, going to there. And when you read this, you're starting from here, going to there. So one way is going left to right, the other way is going right to left. Okay, we played with those. So those are two things. These are the tools or the parts of the game in order to actually talk about what a Markov chain is. And then the last part of the game we saw the other day, that was the Markov property. And that's sort of long, but it's, you know, I've got to at least say what it is. It says that if you find the probability at day n plus 1 that you're at some state I n plus 1, and you know a lot of stuff, you know where you were day 0, you were at state I0, you know where you were at day 1, you were at state I1, etc. You know where you were all the way up to day n, you were at state IN. And you want to know the conditional probability of knowing where you were in the past, of being at this state the next day. That can be done by just excuse me, canceling everything in the past. The only part that's really relevant is where you were one step back. So that's the Markov property. And this has to hold. There's a bunch of quantifiers that you have to put in here. This has to be true for all states, I0, I1, I2, all the way up to IN and IN plus 1. And for all different n. So you could know, you know, where you were the first 10 days or first 100 days, the same property would hold. So the way that I look at this is a very simplifying property, because this conditional probability would be very complicated to calculate. This one is not so bad because it only depends on one event rather than so many other events. Okay. Now, there's two ways. Well, anyway, this is a summary of what we've done for the two-state Markov chain. There's two directions to go now. One direction is to go to more states. So this is fine as an introductory example. It's probably the simplest example of a Markov chain that I can talk about. And I've been talking about it now for almost 2 weeks. Not quite. But there are Markov chains that have more states. Now, the good news is, even if we have more states, all the ideas given here for the two states still go over. We're still interested in knowing where we are initially. So there's an initial distribution. There are transition probabilities, these guys, but there are more of them because there are more states. And so you have arrows flying all over the place. But, you know, it's the same idea, just more of them. And the Markov property remains the same. It turns out we can do a lot without the Markov property, and we did a lot without the Markov property. What did we do? We found the distribution on day n in terms of the distribution, the initial distribution. And we did that just using probability multiplication rule and sum rule. We didn't use the Markov property. When do you need the Markov property? You need the Markov property when you want to do joint distributions. And that's what we were getting into a little bit last time. Good place for me to pause and see if anyone has a question. Any questions? Okay, let me see if I can move this up a little bit. All right. So, so we can go to more states, and that'll be more complicated models. And we were beginning to see that yesterday, or not, I'm sorry, the day before. One of the problems there had us picking balls out of a container and switching them, and we had more states there than just two. So we got a little glimpse of that the other day. But what I think I'd like to do now, since I've invested a little time on the two-state guy, the cool thing about the two-state Markov chain is the basic ideas are there. And And if you're going to be talking about the basic ideas, which is where we are in the course, we're at the early part of the course, it makes sense to talk about the simplest example you could have. Now you could say, well, isn't a simpler example one state guy? Well, yeah, but then you're not going anywhere. That's too simple. It's dull. You're just at one state and you're never going to be anywhere else. And so there's not too much to say about the one state Markov chain. So the first non-trivial example is the two-state Markov chain. And I think what I want to do now is bring in the idea of matrices, which have not really been addressed yet. I'm trying to think, have we done anything with the matrix? Not much. So let me go through further description of the two-state Markov chain with introducing now how matrices can help us understand this thing better. So the matrix that I want to introduce is the following. So I want to introduce this matrix P, it's capital P. And in this case, it's 2 by 2. And it just has it within it these transition probabilities. So in the first upper left-hand corner would be P00. And over here would be P01. And this would be P10. And this would be P11. Okay, since it's made up of the one-step transition probabilities, I guess I should have said these are one-step transition probabilities. And since this matrix is made up of this, it's natural to call this the one-step transition probability matrix. So this is the one-step transition probability matrix. This is the way your book writes it. Not everyone writes it this way. Some people put in this position, they put the 1, 0 entry. And so they reverse these two. But I'm sticking with our book and our notation. So I'm going to look at this. And since the states are 0 and 1 here, there's only 2 states. But they sort of go along with how we usually describe matrices. That is, a matrix A is usually described as A11, A12, A21, A22, where the Aij entry, the I is the row, and the J is the column. Okay, so this would be in row 1, column 1. There it is. This would be in row 1, column 2. That's describing where this is. This would be in row, well, I guess that got to be 0. This is row 1, but row 1 in this case is in terms of 0. So it's a little different than here, right? Usually when you do matrices, you don't start at 0. You start at 1, 2, as I show here. But this thing is indexed in a different way because our states are 0 and 1. So 0, 0 would be in the, let me just say in the first row and the first column. I won't call it row 1. I'll just say the first row. And this one is in the second row because of this 1 and the first column. Okay. So there's a little disconnect. Instead of having indices 1, 2, we have indices 0, 1, but I don't think that'll confuse too much. Now we could, in this case, we could replace these things by what they are. So we already said P00 is 1 minus P. And we said P01, we just scroll up, is P. P10 is Q. And P11 is 1 minus Q. So just using the information that we have from here, which really was what we used over here. Why did we use P's and Q's? P's and Q's is a little simpler than writing these things. There's a little more cumbersome. Turns out all the transition probabilities here can be described in terms of just 2 probabilities, P and Q. So we did that, and if you want to transfer that to the one-step transition probability matrix, it looks like this. Okay. Properties. There are some properties of P. So let's note property, note. Capital P is called stochastic. By the way, stochastic is just a fancy word for random. So when you study stochastic processes, that's the name of your book. But you could have just called them random processes as well, and some people do. Well, what does it mean when you're talking about a matrix being stochastic? 2 things. It's made up of probabilities. Well, that we already knew, because all of these P and Q and 1 minus P and 1 minus Q are probabilities. But it's what makes the matrix stochastic is the rows add up to 1. So if you look at the first rows, the 2 P's cancel, and you just get, if you added them, you just get 1. And here the 2 Q's cancel, and if you add them, you just get 1. So a matrix is called stochastic if its rows sum to 1. Okay. And in this case, P is definitely a stochastic matrix. Questions? Well, yeah, go ahead.
Oh, sorry. I had a question about the matrix.
Mhm.
How are the entries positioned again? Can you explain that?
Well, they're positioned according to this description right here. So the first entry would be the 0, 0 entry. And this would be the 0, 1. So if this is 0, 0, 0, 1, the second index is going up by 1. That means you're in the different row, you're in the different column. If you want to think of this, I don't like thinking of it that way, but if you want to, you could think of this as row 0, column 0. It's easier to think of it as first row, first column. And then this one would be still first row, second column. And this one would be what? Second row, second column. So you sort of think of where these are in terms of rows and columns. And what they are, well, as far as what they are, they're just what we already have been talking about. They're these guys. Did I catch what you're asking or not?
Yeah, I guess my question was, what if the first entry in the upper left was 0, 1? Or is that even possible?
It won't be for us.
Okay.
So the rest of the way, this entry will always be in the first row in the first column. And if, well, it depends how our diagram looks. If our diagram looked a little different, suppose our diagram, instead of going from 0 to 1, went from state 1 to 2, but everything else was the same. this would still be P, this would still be Q, this would still be 1 minus P, and this would be 1 minus Q. But our matrix now would be indexed by the states 0, 1. So it would have here, you would have P1, 1. And over here, you'd have P1, 2. Whereas here you'd have P2, 1, and here you'd have P2, 2.
Oh, I see what's going on.
Yeah, and that's more the way things usually are done for a matrix in terms of index 1 and 2. The only reason it didn't happen that way is our states were 0 and 1 rather than 1 and 2. Does that help a little bit?
Yeah, I don't know why I thought you were just randomly choosing entries.
No, I'm not randomly choosing. I'm looking at the states. And so these probabilities represent, well, just what I have up above. They represent going from one state. It's a conditional probability of going from one state to another state within 1 day's time. And so these are the things that populate the matrix. And this is the customary order. And if the diagram looked like this, then it would be a little more aligned with what you've seen in linear algebra. Okay, well, a reasonable question is, okay, you put all these transition probabilities into a matrix, what good is that? Or why do we want to do that? Well, let me give you a reason for doing that, okay? Because I mean, there must be a good reason. We're not just doing it just to give you another picture to look at. So there is a reason. Let me talk about it. Suppose, well, let's review this. We already said that pi 0 is the initial distribution. I'm going to make that a vector. Where was it? It was defined up here. There it is. Well, I didn't define it, but I did give its table. So pi 0 is going to be the vector that has these two numbers as components. So I'm going to write it as pi 0, 0 and pi 0, 1. Well, okay, so there's a little more notation here, but we already know what these mean because the subscript on the pi's tell us that we're at the initial day, which is day 0. And 0 and 1 tell us the probability. So what does this mean? This is the same as saying the probability that on day 0, you're at 0. And this guy is the probability that on day 0, you're at state 1. So this is what this means. And this is what this means. Now we have talked about that before, and I've called this the initial distribution. And again, there's a little bit of a disconnect because you might think of the initial distribution being you might think of it as being day 1. But in the context of this book and many books, this is day 0. So initial means time 0. And that's what makes this a little confusing. This subscript is the time. So the initial day would be day 0. This 0 is the state 0. So there are different zeros that occur in this thing. And if you record it this way, this says the probability at day 0 that you're at state 0 is the first component. And the probability that at day 0 you're at state 1, that's the second component. Well, if you put the two things as components in a vector and put on brackets, this would now be thought of as a vector. So I introduce the arrow. So this is the initial distribution, and or if you want to be a little more accurate, it's the initial distribution vector, right? It's still the initial distribution, and when we write it this way, then it looks like a distribution table or a probability table. But if you take these two components and just make it a row vector, which is what they're doing, then it's natural to call this the initial distribution vector. Okay. So again, this is a move in the direction of linear algebra. Why? Because we've now got a matrix and now we've got a vector, right? These are all things that you've seen in some elementary linear algebra class, hopefully. What would pi 1 be? Well, it makes sense. This would be the distribution on day 1. So that would be this guy, pi day 1, the chance that you're at 0. Day 1, the chance that you're at 1. Or if you want to write it in terms of what it means, the probability that at day 1 you're at 0. And this would be the probability that at day 1 you're at state 1. So what would this be? This would be the distribution vector. Distribution vector 1, which is not the same as the day 0. Be careful. Okay. Okay. Well, I mean, there's nothing to stop us from doing this for every day. So pi 2 would be similar. It would be pi with a subscript here. And it would be, if this helps you remember, the probability on day 2 that you're at state 0, and the probability on day 2 that you're at state 1. So this would be the distribution vector day 2. And if you were to do this in general, how would it look? You'd have a distribution vector at every day possible. So it would be on day n, the probability that you're at state 0, and then day n, the probability that you're at state 1. And so that means this, the probability that on day n, you're at state 0, and the probability that on day n, you're at state 1. And this would be the distribution vector on day n. So I've got a bunch of different vectors, okay? Well, let's redo the calculation. Oh, this would have been pi sub n, somehow got lost or taken away. I see things are missing here. So the usual games with my OneNote. It's, if I stare at it the wrong way, something disappears. So hopefully you're taking it down as we go along. Okay, so question, how do you get pi 1 in terms of pi 0? Question. How is pi 1 related? Okay, so the easiest way to do that is what we've already done before with the trees. So here's the answer. make a probability tree. So initially, you're either at 0 or 1. And as the next day comes, you either transition to 0 or 1 again. So let's say the probability of being at 0, well, that would be pi 0, 0. So the probability that you're here on the initial day would be pi 0, 0. And the probability that you're here on the initial day would be pi 0, 1. Those are the probabilities that on the initial day you're at those states. And then these are transition probabilities. So this would be the probability of going from 0 to 0 in 1 day's time. And we already saw from our picture, maybe I should just lift the picture. The picture is this. P and Q. And 1 minus P and 1 minus Q. So those are our transition probabilities. So the transition of going from 0 to 0 is 1 minus P. The transition going from 0 to 1, you can just find the arrow, that's just P. The transition of going from 1 to 0, that would be starting here, going here, that's going to be Q. And the transition of going from 1 to 1, that's 1 minus Q. So we've seen this tree before. It's going from one day to the next. And in this situation, we're going from day 0 to day 1. So what we're after are the probabilities in this. So let's actually make the table where we are at day 1, where you're either at 0 or 1. The probability that you're at 0 on day 1 goes in there, and the probability that on day 1 you're at 1 goes here. And the probability that x1 is x, where x takes value 0 or 1. Okay. So when I ask how is pi 1 related to pi 0, I'm asking what is this thing equal to in terms of pi 0? Well, it's not hard to figure out, because on day 1, if you want to be at state 0, you're either here or you're here. In other words, on day 1, you're at 0, and on the initial day, you were at 0. In other words, you went down this path. Or on day 1, you're at 0, and initially you started at 1. There's only 2 possibilities for where you were on the initial day. And the multiplication rule tells you how to do this. It tells you the chance of traveling down this road would be equal, well, would be equal to what? So I can squeeze it all in here. Pi 0, 0. Multiplication rule says multiply the numbers along the path. So it's that times that. That's the chance you travel down that road. But then you could also get to 0 by traveling along this path. And since it's an OR, you add. So that would be pi 0, 1 times what? Q. So the sum of these 2 terms is this. Let's do the next one. What's the chance on day 1 that you're at state 1? Well, you're being at state 1 means you either ended up here or here. And the only way to end up at state 1 on day 1 is to either have been on the initial day, you were either at 0 and you went to 1, or you were at 1 and you stayed at 1. So the only 2 ways that can happen would be to travel the paths that I've marked with a star. And again, we know how to figure those out. The chance of going down this road is pi 0, 0 times the transition here, p, plus the chance of traveling down this road would be pi 0, 1 times q. Okay, so the question was, how is pi 1 related to pi 0? And the answer is this, because this part here, well, let's do the last one first. This one would be what? Pi 1, 1. And this part over here would be pi 1, 0. So here's how to get pi 1 in terms of pi 0 by using this little tree and using the multiplication and the sum rule. The multiplication rule says as you go from start to finish, you multiply the numbers along the path. The sum rule says if there's more than one path to travel, you do one and then add the component from the other path. Okay, so we've done this. Yeah, please.
For the second equation, shouldn't it be pi state or pi day 0 state 1 q or 1 minus q instead of just q?
You know, I think you're right. So let me go back and redo this and make sure I did it right. So the first part, you're talking about px1 equal 1, right? Are we together?
Yes.
Okay, so to get there, to get at 1, you got to either go this way, which would be pi 0, 0. So that part is okay. Times p, that part is okay. But then the other one should be pi 0, 1. And it is. But it should have been times 1 minus q. That's your correction, I think, right? And I think you're right.
Yes. Yeah, that's what I was talking about.
Yep, I agree. Thank you for bringing it up. See, a correction like that's so important because if you don't bring it up and no one else brings it up, everyone writes the wrong thing. And if they look at it later, they don't know what I was doing. So thank you so much. Appreciate it. Yeah, so, and if you were wrong, then that's fine. And we're communicating, and then I'm right and you're wrong. And that's okay too. But either way, it's nice to get it right. All right, so this answers the question, but this is a little complicated. What's complicated about it? Well, in order to find the components of pi 1, you got to make this little tree and do this little dance and figure out where you want to be and use the multiplication rule and the sum rule. It's correct. There's nothing wrong with it. It's correct, especially now that it's corrected. But it turns out there's another way to remember this, which is maybe an easier way. So let me show you the easier way to think of it. The easier way to think of it is the following. Take the matrix, which we haven't used yet for much, this guy. All right, so the matrix looks like this. But I'm going to take this form where I already put the p's and the q's in there. So 1 minus p is in the first row. 1 minus p, and p is in the first row. And this was q, and this was 1 minus q, right? So this is the matrix P. And now I'm going to ask you to think about what happens when you multiply this matrix, and this is a little weird, on the left, not on the right, by pi 0. Well, pi 0 has entries pi 0, 0 and pi 0, 1. Okay. So I'm saying consider this product. Now, I must know something or we wouldn't be considering it. So it's got to be relevant to what we've been doing. But at this point, it could seem like it's coming out of the blue to you. Let's look at what the product is. Now, remember, this is a vector, but a vector could be thought of as a matrix if you want. It's a matrix that looks like it's what, one by two. It's not a square matrix, it's a rectangular matrix. But all right. So this is 1 by 2, which is the dimensions of it, and this thing is dimension 2 by 2. When you multiply a 1 by 2 matrix by a 2 by 2 matrix, what comes out? Well, you retain this dimension of 1 and this dimension of 2. So what comes out is a 1 by 2 matrix, which you can think of as a vector if you want. Okay, well, let's figure out what comes out. Except I'm going to have to leave a little more room than I've left so far. So how do you multiply matrices? You multiply this times that. So I'll do it. Pi 0, 0 times 1 minus p. Keep me honest. And then you do this entry times that one. Plus pi 0, 1 times q. That's multiplying this row times this column, essentially. And then you do the same thing, multiplying this row by the second column. So that would be pi 0, 0 times p plus pi 0, 1 times 1 minus p. Okay, so I've multiplied these two matrices together and I've obtained this. What I want you to do is compare the two entries of this with these entries up here. I'm claiming that what I've got is really pi 1, 0, comma, pi 1, 1. Well, okay, so we just compare. Pi 0, 0 times 1 minus p, check. Pi 0, read it, okay. Let me see, what was that? That was pi 0, 1, I believe. Pi 0, 1 times q. So the thing that's encircled here is the same as this. And if we go on and look at the next entry, pi x1, so, and by the way, this was pi 1, 0, so we've confirmed that these are both the same. That's equal. Now what's over here? Pi 0, 0 times p, pi 0, 0 times p, plus pi 0, 1, 1 minus q, pi 0, 1, 1 minus q. So this thing in the box equals this part. So this is another way to sort of mechanically get, and so what would this be? This would be the vector that we're calling pi 1, which has components that look like this. So what are we saying? We're saying if you want to get pi 1, let me reverse the order here. If you want to get pi 1, take pi 0 and multiply it on the left by p. This is the matrix P. And we've just confirmed that it works. Why? We already figured out how to do it using probability table and or tree and all of this. So we already knew what pi 1, the components of pi 1 were. Pi 1, 0 was this, and pi 1, 1 was this one. And we just compared it to what you get when you multiply this matrix by this way. So this matrix multiplication, though it may not be obvious at first, is doing the same business that we're doing on the tree over here because it's coming up with the same answer. Now, well, that's part of the main thing I'm trying to get across today, is that you can find pi 1 by multiplying p by pi naught in this manner. Now, what makes it really useful is it works if you wanted to get pi 2. What works? Well, what you should do is take pi 1 and multiply it by p. And the whole thing works again. Now, why would that all work again? You can go through it all again if you want. In other words, you can use the tree argument here. Instead of calling this first initial segment pi 0, call it pi sub 1, right? Because that's what's known now. And then the P would still be the capital P would still be the transition probabilities. So the tree would look almost the same. The second stage would be identical to what it is. The first stage would be the same, except the subscript would change from 0 to 1. And in order to find out pi 2, in terms of pi 1, you can go through the exact calculation on the tree, figuring out the two check paths and figuring out the 2 stars paths. And this thing will still hold, except what? Except wherever you have a subscript on pi of 0, put a subscript of 1. So in other words, the argument that led to pi 1 from pi 0 works just as well going from pi 1 to pi 2. And if you don't believe it, try it. And so you can duplicate this part of the calculation. And then it's pretty easy to duplicate this part of the calculation. Just replace the components of pi 0 here with pi 1. And if you do, you'll see that you get what pi 2 is from the first part of the calculation. So what I'm arguing here is this is true, but not only this is true in general. So let's do the in general part. In general, if you want to know the distribution on day n, you can find it by finding the distribution on the previous day. Well, why don't we make this day plus 1? Then the previous day would have been n. Okay. Take the distribution on day n and just multiply it in this sort of unusual way. Unusual because you're not multiplying this matrix on the right, you're multiplying it by the left. But it still works the same way. Let's do this. Now, we can put these together and get some interesting results. If pi 1 equals pi 0 p and pi 2 equals pi 1 p, we can now write pi 2. Well, from this, we can write it as pi 1 times p. But pi 1 is this, so we can substitute that into here. So that would get us pi 0 times p times another p. And if you read it from, well, start to finish, pi 2 would be what? Pi 0 p squared. What is p squared? P squared, oh, I lost something. See if I can retrieve it. Okay, I retrieved it. Now I've got to share it. Shared it, but I don't think you got it yet. Straight in and try again. Okay. Share this. Okay, can you see it all again? I hope.
Yeah.
Okay, guess I lost it. I had to do some footwork to retrieve it. Okay. But what the last thing we got is still here, fortunately. It's this. So summarizing it, pi 2 is pi 0 times p squared. That's the part. Yeah. So let me see what I did here. This is this, but we replace pi 1 by this. So it's this times this. And that gives us this. And in general, what does it say? If you want to find the distribution of this thing at day n, it's going to be the initial distribution times p to the n. That's the result. Let me do this again. Yeah, I don't even know. Maybe. Pi2 is pi1 times p. And pi1 is pi naught p. So that's how we get this. Okay. So here's the takeaway. Right on it, right on the cue for the end of the class. So if you want to find the nth distribution, it's now a linear algebra problem. Find the matrix P, take the nth power of that, and multiply it on the left by pi naught. And that'll get you the distribution at time n. Now, we haven't done very much with Markov chains that have more than two states. But what I'm going to ask you to believe, because I don't think I want to do it in total generality, I want you to believe the result still holds. So even if P is not 2 by 2, which it would be in the two-state guy, in other words, the P is equal to this thing, even if there were more states, and this was like, 3 by 3, 4 by 4, whatever, all of this linear algebra and all of this probability rules lead to the same result. Now, you can say, well, is this really better than just doing it one step at a time? Well, yes and no. The no is, it's no fun to take a matrix and multiply it by itself over and over again. That gets old quickly. However, there are computer algebra systems, such as Wolfram or Mathematica or a lot of things like that, that you can just give a matrix and ask it to find the power of the matrix, and it does it for you. That's a common thing that people want to know when you deal with algebra, linear algebra. They want to know the power of a matrix. So if it does that for you, then it's easy just to multiply that matrix times some constant initial one. So for example, well, we could redo what we did before. I think before we found out what pi1 and pi2 were without using this matrix representation. We just did it using the rules of probability, the tree, and so forth. But now you can use these things and sort of make quicker work of it. There's a problem in the back of the book that I think we can look at now. So if we turn to page 43, problem 12 has a three-state Markov chain. And they're asking you things that are related to this. They're asking you to find p squared. They're asking you to find p to the fourth and some p to the n in general. So why don't you try that problem for homework? Homework. Page 43, number 12. And I think I'm pretty much done. I'm trying to think if I want to tell you one other thing. Yeah, I think I can tell you one other thing without convincing you of it. So this one we got through, and I sort of went through the explanation. I hope it makes some sense. But it turns out, so here's a result we'll talk about next time. It turns out p to the, how can I describe it? Let me stay in the two-state guy. So suppose you're in the two-state guy and you're just looking at squaring. If you square the transition matrix, it turns out to have its own meaning. And let me tell you what its meaning is. I'll do it in 2 steps. 0 to 0, 0 to 1, 1 to 0, 1 to 1. But in view, well, this is squaring P. But this turns out to be something that's not so obvious, but it is really nice. It turns out to be the probability of going from 0 to 0 in 2 steps. 0, oh God, I had to find that. OneNote has no sensitivity to timing here. Let's see. Okay. All right. Let's see if I can see it again. Okay. And naturally, I've lost some of it. Okay, so I'll try to write this again and hope it doesn't flake out on me. Going from 0 to 0 in what we'd say 2 steps. Going from 0 to 1 in 2 steps. I give up. I give up on that screen. I haven't given up on the whole thing. So again, let me try it one more shot. Okay, it doesn't like it. I know that.
It knows class is over.
Yes, exactly. It's timed. That would be funny. Okay, let me go to another page. That's what I need to do. I'm just going to go to another page because this page is not my favorite. Let me see. Bear with me. I mean, I've got this one line to do. I've got it, but I don't have you on it yet, so I got to share it with you. Come on. I'll give you a break. I mean, I really can't complain too much because it would do me anyway. Let's see. All right, one more time. Let's hope it holds, but we got clean page, so I think our chances are better. What am I talking about? I'm talking about if you square this guy, which is this. Wow, it is unstable. If you square this guy, what you get is the probability of going from 0 to 0 in 2 steps. Going from 0 to 1 in 2 steps. By the way, this could be confusing. 1 to 0 in 2 steps. Finally, 1 to 1 in 2 steps. Yay. Okay. What do you know and what don't you know? This part you know, we defined what P is. P is this guy, the transition, one-step transition probability matrix. And now we're just talking about squaring it. And now I'm telling you that that turns out to be something cool. This is cool. What does this mean? This means this is the probability of, I'll just write one of them. I think that'll make it clear. Suppose you started off at 0. and 2 days later, you were back at 0. That's going to take 2 steps, right? Because there's day 1 and there's day 2. So this thing is called the 2-step transition probability, because you're going from 0 to 0, but in 2 days rather than 1. So if these were the 1-step guys. So if you want to make sure you don't confuse these with this, if you really want to, you can put something that looks like a superscript on these. There was no need to do it before because we didn't think about going from one place to another. I give up. Okay, it doesn't want it. Let's quit. I'll quit the class. I'll take my short water break and come back and talk about anything else, including problem 12 or any of the other ones that you want to talk about. Sorry for the insensitivity at the end. The screen doesn't want me to go any further. So let me see if I can clear that up. For those who can't hang around, I'll see you Friday. For those who can, I'll see you shortly. Okay. So let me see. I shouldn't have pushed it. Oh, yes. Now I'm getting a nasty note saying that I'm opening and closing this too much. I know that. Okay. Okay, so this is where I was when it left me. And let me see if I can just go with what's here. If you square the 1-step transition matrix, you get the 2-step transition matrix. What are the 2-step transition matrix? I'm just trying to show you the first entry here. Well, I've done it. You start at 0 and you end at 0 in 2 steps rather than 1. What makes this cool and confusing at the same time? Well, it's telling you there's a nice way to get the 2-step transition matrix without counting all the paths. And the way to do it is to square this matrix. That's the cool part. The confusing part is here you're squaring a matrix, which we know what that means. You just multiply the matrix by itself. This looks like squaring also, but it's not. It looks like squaring because it looks like an exponent. It's above the expression, but it doesn't mean exponent at all. What does the 2 mean? The 2 means up here that you started here and 2 days later you were back to 0. Here you started at 0 and 2 days later you were back to 1. Here you started at 1 and 2 days later you're back to 0. So these are not squares. These are descriptions of where you start and how many days later it takes you to get to the next point. So these are called 2-step transition probabilities because it takes you 2 steps to make the move. Okay, so the confusing part is the 2 is an exponent on this side and over here, but the 2 in here looks like an exponent, but really doesn't mean multiply this by itself. You don't want to do that. It really means figure out the chance of going from 0 to 0 in 2 steps. So let's actually do one, see if I can do something on this page without it going away from me. Let me show you how to do one of these. I will erase this because it doesn't. Let's go back to our initial example with numbers because it's easier to convey an idea with numbers sometimes. Our initial example was this. We had a 10% chance of the machine break-in, a 90% chance it would stay working. if it's broken, it was going to be fixed in 3 out of 4 days, and it was going to take, there's only a 1/4 chance that it was going to, yeah, I guess I'm keeping everything decimal, so make it 0.25. Okay. So let's figure out the probability of going from 0 back to 0 into 2 steps. Well, there are different ways that one can do this, but one way is just imagine walking on this diagram. So one way to go from 0 back to 0 in 2 steps would be 0, 0. You loop twice. What's the other way? Well, I guess there's only one other way. You go away and you come back. You go from 0 to 1, and then you go 1 back to 0. So let me see if I want to say this. Here you're going from 0 to 0, and then you're going back to 0 the second time. Okay. So I'm just imagining walking from 0 back to itself in 2 steps. I either loop twice or I go up and go down. The chance that I loop twice turns out to be 0.25 times itself. The chance that I go up and down is 0.75 times 0.1. This should be what you get if you square that original matrix. So let's check. The original matrix was 0 to 0 was 0.25. This is 0.75. This is 0.1. This is 0.9. Square this. I really don't have to square it all because I'm really just interested in the first entry of it. So the first entry of it, well, when you square this, how would you do it? It would be this times itself. And if you want the first entry, you multiply this column times this row. So that means I need to do 0.25 times 0.75. 1 times 0.9, 0.25, 0.75, 0.1 times 0.9. When I square to get the first entry, I would multiply this by this, plus this times this. So that's what you get when squaring, but that coincides with what we got by actually counting. I just counted the 2 ways that there were to do it. If I'm going to go from 0 to 0 in 2 steps, one way is to loop twice, the other way is to go up and down. Each of those have probabilities this, which is agreeing to what you get when you square. So that's sort of giving you a hint of why that it works at least. I'm not sure it gives you a hint of why it works, but it gives you a hint that it does work. Oh, where is it useful? It's even better if you suppose instead of squaring, if you took the nth power of p, that represents the probabilities of going from one state to the other in n steps. So taking the nth power of this matrix has a physical interpretation in terms of probabilities. I'll at least say what it is. If you take the nth power of the one-step matrix, that turns out to get you going from 0 to 0 in n steps, 0 to 1 in n steps, going from 1 to 0 in n steps, going from 1 to 1 in n steps. So these are conditional probabilities. What's the first one? It says if you know you started, for example, initially at 0. You wanted to know after n days later, you're still at 0. If you're going to count all the ways you can go from 0 to 0 in n steps, you're going to get lost in the paths real quick. But the easier way to do that is just take the nth power of the one-step matrix, and that'll get you each of these entries. So that's the result. I haven't explained it that much as to why it holds, but I'm telling you what it says, and it's pretty useful. Questions on any of that? Cool. Okay, now let's get to the office hour. Questions in general, any requests? I'm willing to look at homework, new or old, or any questions about including in class. I'm good with that too.
Yeah, I have a quick question with when you take p to the n, the entries in each matrix, how do those, can you rewrite any of those or relate them to like joint probabilities?
You're asking about this equation right above here, more or less?
Yeah.
So you're asking me, can I relate these with each other in some manner?
Yeah, because I guess I'm just trying to think if there's like a way to express them in terms of like joint probabilities as well.
Let me think about it. There's a connection between them.
Yeah.
So there's this connection. It's not so much a joint probability, but basically if you're going to, well, we're still in just the two-state guy. So that makes life easier. Okay, so we're in this guy, P and Q here. P and 1 minus Q. So if you're at 0, after n days pass, where are you going to be? There's only two possibilities. You're either at 0 again or you're at 1 after n days. So one relationship here is this matrix is also stochastic. In other words, this probability and this probability add up to 1. And the argument is what I just said. After n days, you're either at 0 or you're not. And not means you're at 1 because there's nowhere else to go. So these are still stochastic, which means what? Pn00 added to Pn01 is still 1. But that's not giving you a relationship so much about, yeah, it's not doing what you're asking because you're asking for joint. In joint, this is only information. Well, let me think about that. It's really information of where you are after n points, after n steps. And but it's conditional information, assuming you started at 0 or assuming you started somewhere else. So I think it's, as it sits right now, I don't think it's going to give you information about joint distributions. It's going to give you more just what I've been talking about, the distribution at date n.
Okay.
Yeah.
And yeah, for the original one-step transition probability matrix as well, is there any interpretation we can make out of that if we look at its eigenvalues?
Oh, that's a wonderful question, and it's got a, yes, it turns out that looking at, so you're going back to the original one. So let me go back. Let me go back to the original one. If you're interested in that kind of stuff, and who's asking this question? Let me see where it's coming from.
Raymond?
Raymond, yeah. So let me sort of get to what I'm hearing. Maybe it's easier just to write it down here instead of erase. So the question that I heard is that if you have P, which is P00, P01, these one-step guys, P10 and P11. And do the eigenvalues add anything to the discussion, or does it help us in some manner? And the answer is yeah. But where it really helps is, so I don't know how many of you know what eigenvalues are. Eigenvalues for a matrix, let me just quickly say so that we're all together. You have a matrix M and you multiply it by a vector V. Sometimes, not always, but sometimes what you'll get is a constant times the original vector. Okay. The lambda in this case is that constant. And so what we're saying is sometimes for a certain matrix, if you multiply that matrix by a vector, you'll just get a scaling constant times the vector. So the vector that comes out is really in the same direction as the original one, but it may be half the length or twice the length, or even negative the length or something like that. If that happens, lambda is called an eigenvalue and V is called an eigenvector, assuming V is not zero. So we're talking about a vector here that's not a zero vector. And that's something you would see in a class on linear algebra. I don't know how many of you have seen it, but clearly Raymond has. He's asked the question. It turns out finding the eigenvalues of a matrix are very useful in many ways. And related to what we're talking about here, why that's a good thing to do is if you know the eigenvalues of a matrix, finding its power is easier when the eigenvalues are known. Now, you can say, well, how could it be easier? Well, if you don't know the eigenvalues, I mean, the way to find this is just the old-fashioned way, multiplying p by itself n times. But as I've indicated, that gets old quickly. It's probably better to do it on a computer algebra system like Mathematica or Maple or something, Wolfram. But even there, if the matrix is high dimensions, it loses accuracy after when n gets large. So knowing the eigenvalues is a real good thing in order to find p to the n. And p to the n is something which we're interested in doing from what I just said, because p to the n becomes these n-step transition probabilities. So yeah, that's a good thing to do. That's a rather general answer to your question. I hope it helps. So.
Mhm.
Anyone else have a different question or similar? Doesn't matter. I'll take a request. If you don't give me a request, I'll give you sort of a different problem just to play with. I'd rather take requests, assuming that you have some. But if you don't, that's fine. I'll just give you a little related problem here to think about. Okay, since I got no other problems being asked, here's one for you. Let me get a clean page. Put lines on it. So I'm not quite done with the linear algebra stuff we're doing, but suppose we have a three-state Markov chain. And one question is, well, how do we know when we have a Markov chain? And so that's a reasonable question. You need states, and you need transition probabilities, and you need the initial distribution. So these are things that we said at the start of today's lecture, you need an initial distribution. You need transition probabilities. And you need the Markov property. The Markov property is really needed to get information about the joint variables. So let's just see how this might work. Suppose you had a 3-state guy. Let's do a takeoff of the one that we did in class. So suppose you had 3 states instead of 2. And let's assume again it's a machine. And suppose 0 is the machine is broken, it's not working at all. And 2 means it's working. And 1 means it's on the blink. Okay. So maybe it'll work sometimes, but maybe it won't work at other times. So it's sort of in a in-between state. So this is a natural generalization of what we've been talking about, because in class we've been talking about a machine that's either working or not. Now we've got a machine that's either working. So 2 means it's working. That's fine. And 0 means it's broken. It's not working at all. And 1 means it's works sometimes works, but not all the time. Okay. Well, I've dealt with printers like that, and there are old cars that are like that too. Sometimes, if anyone here deals with old cars, sometimes they work really well, and sometimes if the weather's not good or some weird conditions happen, they don't work, or they work sort of off and on. So there are a lot of things in the world that are modeled like this. Let's try to do what we did before. Let's suppose that if it's working, let's suppose it'll still be working. But let's say there's an 80% chance of that, and there's a 10% chance that it'll be working in a spotty way, and a 10% chance that it breaks entirely. So what am I doing? I'm creating some, quote, reasonable transition probabilities. I've got a machine that, if it's working, seems to be working the next day, 80% of the time. 10% of the time it breaks, and 10% of the chance it goes on the blink. And so it's, works sometimes. Okay, let's suppose it's broken. What's the chance that it's repaired? Well, I mean, it could stay broken. And suppose that's what we had before, which was like 25% of the time the repair person didn't get out to fix it. But now there's 75% of the time, and suppose they come out and fix it, and suppose that works. But it doesn't work 75% of the time anymore. Maybe they don't fix it. Maybe they don't really fix the problem. So maybe this is like 60%. And so there's a 25% it wasn't repaired at all, and a 60% chance that it was repaired so that it works. The only other possibility is that it's better than it was, but it's still on the blink. And that could be something like what, 15%, 0.15. I'm making these up. Okay, I'm just making up an example. What's the primary purpose? To get something that's not a 2-state thing. And this seems like a reasonable kind of thing that this Markov chain can model. Okay, so we know from 0 where we're going. We're either going back to 0 to 1 or to 2, and we know the transition probabilities. And from 2, we know where we can go. We're either still working on the blink or broken entirely. But we haven't described what happens at 1. Well, suppose at 1, it only works intermittently. And I know what that means. That means it's going to break again, because usually things like that go like that. So maybe there's a good chance that it's really going to break. 60%. And maybe they'll continue to function on the blink. But then there's also the miracles, which happen sometime, okay, which is it fixes itself. For me, fixing itself is usually a result of turning the thing off and turning it on again, and whatever hang up it was having, it somehow clears it. Okay. So there's only a 10% chance of that. Now you see how these numbers have to be chosen. There have to be probabilities. They have to add up. From any state, all the probabilities have to add up to 1. Because otherwise it doesn't make sense. If this thing is on the blink, either it's going to break, or it's going to stay on the blink, or it's going to get well. And together that should be 100% of the time. Okay. So now we have this. So we have the transition probabilities. We could assume the Markov property. So this is usually what we assume. Why? If we don't assume it, then we're not talking about what we're talking about in this class. Well, the chapter is Markov. I don't know, what is the chapter? Markov chains, I think. Yeah, Markov chains is chapter 1. So for this class, for now, we're assuming the Markov property. So, okay, I'll put a check next to that. And the only thing I haven't described is the initial distribution. So the initial distribution would be the probability that it's either in state 0, 1, or 2 on the initial day. And, you know, maybe you really don't know this machine at all. It belongs to a friend or something. So if you really don't know the machine, maybe it would make some sense to assume that the initial distribution, let me make it in vector form. Maybe it's like a third, a third, a third. That would be pretty sad, because it would mean what? A third of a chance it's down, not working at all. A third of the chance it's on the blink, and only a third of the chance it's working. But I mean, this is usually what people might assume if you really don't know the machine at all. You don't know how old it is or anything. You just might assume there's a uniform probability. So the chance of any of these happening are the same. They're 1 out of 3. If it's different, if you think the machine has a better chance of working, which we did before I think we had the chance of the machine working be 90%, then you could reflect that in the initial distribution. This could be made usually with your knowledge of the machine. Okay. So now this is a Markov chain. It turns out that if you fulfill these 3 conditions, figure out the initial distribution, figure out the transition probabilities, and assume the Markov property. So what do you need to get rolling here? You just need a diagram with states. You need arrows going between the states that represent probabilities, transition probabilities. And you need an initial distribution. Now, if you wanted to put it in terms of the matrix, that would be easy to do from what we did today. It would be a 3x3 matrix. So the first state would be going from 0 to 0. And the chance of that would be the 0.25. From 0, where can you go? You could go to 1, and the chance of that happening would be 0.15. And from broken, you could get repaired, and that happens 60% of the time. From 1, the chance that you break is 60% of the time. The chance that you're on the blink and you stay on the blink is 30% of the time. And the chance that it magically cures itself happens 10% of the time. And if the machine is working, the chance that it goes bad is only 10% of the time. That's pretty good. But there's a 10% of the time that it goes on the blink, and then there's an 80% chance that it still works. Those are the transition probabilities, and we put them into the 1-step transition matrix. And what would pi 0 be? Well, we just used the vector notation, so why not adopt it? Got it right here. 1/3, 1/3, 1/3. It's a little weird to have this in fractions and have this in decimals, but it happens. Something disappeared. 1, 2, 5, 4, 9. Okay. What could you be asked about such a system? The natural thing would be to be asked about maybe what pi1 is, pi2 is. Maybe pi5. And with what we did in class, assuming what we did in class transfers to any Markov chain, and it does, to find pi1, all you'd have to do is to do what? Take pi0 and multiply it by 2. That's what we covered today. And to find pi2, take pi0 and multiply it by what? P squared. And this one. And, you know, I'm almost tempted to call this future homework. I didn't get far enough in class to do this, but I've gotten it down now. And if this is future homework, how would I ask you to do this? So I'd probably ask you, you can do it on a calculator, I'm sure, if you've got a calculator that deals with matrices. Because if you have a calculator that deals with matrices, it should be able to square them. And it should be able to raise them to the 5th power. So all of these algebraic expressions should be known. And then you got to do some, you know, interesting things. So whatever, well, to do this one, it would be what? 1/3, 1/3, 1/3 times the matrix P, which is this guy. 5, 1, 5, 6, 6, 3, 1, 1, 1.8. I don't want to do the number crunching, but you could do it with a calculator quite easily. Just multiply this row times this column. Get the first entry, multiply this row times the second column, get that entry. And then multiply this row times the third one and get the third entry. And when you do that, that's going to be pi1. That would be the way I would recommend doing it. I wouldn't want to go back to the probability tree, not because it's wrong, just because it's longer. And once we understand that these equations hold, this is the advantage of using linear algebra. And by the way, using the probability tree, the trees would be worse than they were before. Why? Because before, we were either working or broken, or broken or working. So we had trees that look like this. This time we have 3 possible branches, 0, 1, or 2, broken, on the blank, or working. And there'd be 3 different branches coming out of each of them. So what am I suggesting? It could be done, but it would just be more work. And I think it's to your advantage to get used to the linear algebraic way of doing this stuff. Okay, so what's the takeaway? The takeaway is sometimes students ask, well, I don't even know where Markov chains come from. My answer to that is it comes from satisfying these 3 assumptions. Find some transition probabilities from going from states to the next. You can either make them up or they could be given to you by reality. Put on an initial distribution. Again, it's either given by outside statistics, or you can make it up. And usually we assume the Markov property holds. Now, in general, There are times the Markov property doesn't hold, so we're going to have to talk about that later. But if you assume it does hold, the takeaway is what? Most things that you're interested in can be figured out in terms of this transition probability function and the initial distribution. So it's sort of neat. It means these are the key elements you need to do stuff with this. You need to know the one-step transition probabilities. You need to know the initial distribution. And if you know those, you can find a lot of other stuff. Okay, I don't know if that makes some sense, but I thought I'd get it in. That's about all I have. If anyone has a question, I'm happy to go with your question. Otherwise, next time, I guess. I guess I should say today is the last day to do what? To add a class. But I think everyone in this who's here is already in the class, I hope. I don't know when the last day to drop. Anyone know that?
Today is the last day to add and drop.
Oh, so after this, but you could still drop later and get a W, right?
Yes.
So there's a period of time for that. And by the way, W's are not bad. Oh goodness, I've got a phone call here. Anyway, I think I'm going to run off. If anyone has a question, linger on and I'll try to answer it. Otherwise, I'll catch you on Friday.
Thank you.